Okay, thank you very much for coming and invitation to talk. I'll today talk about Chern classes of Schubert cells and varieties, and I should confess that I don't know that much in general about the theory of Chern classes, and even less about all these intricate combinatorics and geometry of Schubert varieties in Grassmannian. But nevertheless, I'll try to tell you one or two interesting facts known about positive Chern classes of Schubert cells and varieties. So I was taking a course by Bill Fulton at my last semester in Michigan, and all the interactions between the combinatorics and geometry that you find inside the Grassmannians looks so very beautiful. So I thought that it would be wonderful to work on whatever project I can find on this Grassmannians. And then I Googled the papers referring to this Schubert varieties in Grassmannian, overwhelmed by this millions of literatures of known facts and questions. So it seemed that everything you could possibly ask about these Schubert varieties were well known or at least very well studied. And then I found this paper by Aluffi and Mihalcea on Chern classes of Schubert cells and varieties. And it was a very charming introduction to me because in the introduction they state that Schubert varieties are among the most studied objects in algebraic geometry, and it may come as a surprise that something is not known about them. So I'll try to tell you what is not known about Schubert varieties in Grassmannians. One fact that's not known yet. So our final goal that we hope to accomplish, but we do not accomplish yet, is to understand the following table. So in the column of this table, you see a so-called Young diagram, this collection of boxes. And I have drawn it into an upside-down way, as it's usually drawn, to emphasize that I'm thinking of homology rather than cohomology. And in the rows of this thing associated to each Young diagram, you see a certain linear combinations of Young diagrams. And there's one term for each Young diagram that's contained in the diagram that you see in the column, and there are certain numbers in front of this diagram. So in this row, you see 1, 2, 3, 5, 3, 4, 1. And these numbers are given by very explicit and elementary formula that I'm going to show you later. But those formulas do not explain why these numbers are positive, for example. That's one thing that we wish to understand. And if there isn't such an interpretation, then we would like to find what these supposed to be positive numbers actually count. So the conjecture of Aluffi and Mihalcea is that the numbers that you have seen in the previous slide are in fact non-negative for any Young diagram. So that is one fact that I want to discuss today. So if you want to prove such a statement, well, in general, how do you show that a certain number is non-negative? There are very, very many ways, but one wonderful way of doing it is to show that your number is equal to some other number, which is non-negative. So that's a wonderful strategy, and you can do it in many different levels. For example, you could show that your number is equal to a cardinality of some set. If you achieve this, then I'm going to say that you have a combinatorial proof. Or maybe in some fancier layer of this argument, you could say that, well, your number is equal to dimension of some vector space and hence non-negative. Whenever you achieve that, I'm going to say that you have an algebraic proof of the non-negativity. So I achieve neither. So we don't have combinatorial proof of the non-negativity. We don't have an algebraic proof of the non-negativity. So I'll give a geometric proof, and you'll see what I mean later. So the obvious questions that remains are whether there are combinatorial arguments which demonstratively shows that these numbers are non-negative, or even you could hope for a statement like that the numbers that you have seen in the previous slide, which are very canonical and natural, are dimensions of some vector spaces. The second curious fact was that this conjecture of non-negativity was stated and proved only for Schubert varieties in Grassmannians. Of course, the same conjecture can be made exactly in the same way for Schubert varieties in more general flag varieties. Whenever you have a B orbit closure in G mod P, you have the corresponding statement or a question or a conjecture. So when I first heard about this conjecture, well, since I knew almost nothing special about this Schubert varieties in Grassmannian as opposed to B orbit closures in general G mod P, I thought that it was very curious that they made the conjecture for Schubert varieties in Grassmannian. So for me, it would be either the case that I could not solve it at all, or if I could solve it, I would have to argue it in a very general group theoretic reasoning which shows the non-negativity for all B orbit closures in G mod P. So the outcome was, interestingly, I was able to prove it for Schubert varieties in Grassmannians. That was the first surprising part for me. And then I figured out that my argument only works for Schubert varieties in Grassmannian and not for Schubert varieties in more general G mod P or G mod B. So I'm going to show you what kind of special property that I need to make my argument work for Schubert varieties in Grassmannians. So the obvious question you could ask is whether these numbers, the same numbers, are non-negative for Schubert varieties in other flag varieties. These are the numbers that determines the Chern classes of Schubert varieties in more general flag varieties. So we have little evidence, but a growing number of numerical evidences that the answer to question B is yes, but still quite little numerical data are accumulated so far. But for some reason, I feel that the answer to the same question should be yes. But if we want to look for counterexamples, then I'll try to point out where should we look for potential counterexamples. In other words, what kind of special properties that are used for the proof of this non-negativity in the Grassmannian case. So I'm going to start from recalling some very basic properties of the story of Chern classes. So I guess the beginning of the story was the desire to count the zeros of a general vector field. So whatever it is, it gives, to me in this talk, it gives an element in the homology group of, say, smooth projective algebraic variety. And it has this property. If you have a sufficiently general holomorphic or algebraic vector field on an n-dimensional variety V, then this homology class is the class of honest zero-dimensional subvariety, which is exactly given by the equation V equals 0. That is finitely many points, and the homology class is given by the number, which counts how many points there are. And it turns out that that number is exactly given by the topological Euler characteristic of your variety, and it does not depend on the choice of your sufficiently general holomorphic vector field. Well, but that equation shows more. So for example, whenever you have a variety where this number, Euler characteristic, is negative, then it shows that there are no vector fields, which is sufficiently general in this sense. So what is needed was that this degeneracy loci, or the points where your vector field vanishes, has the right dimension. So you could do this for any index. So replacing the index n by n minus I, producing a homology class of codimension I, or 2I. So in this case, you have sufficiently general collection of vector fields, Vj, then the homology class that we are talking about is the homology class of an honest subvariety, which is a correct dimension, which is the locus of points where these vectors become parallel. And also you have a dual version of the theory where you have many, many holomorphic one forms instead of many, many holomorphic vector fields. So in that case, up to an appropriate sign, -1 to the n minus I, our homology class is again the honest class of a subvariety, which measures the vanishing of our collection of sufficiently general differential one forms. So the next part of the story is that the same theory can be built up even when your variety does not have enough vector fields in the previous sense or enough differential one forms. That was the theory of Chern classes. And there was another possible generalization in that we are allowing now our ambient variety to be possibly non-compact or possibly singular. So you don't have tangent bundle anymore in the singular case. So you have to be very careful what you mean by a vector field. But anyway, there is a very satisfactory generalization in the direction of part 2. So I'm going to introduce briefly the so-called theory of Chern-Schwartz-MacPherson class. So this theory assigns a Chern class to a constructible function on your varieties. Let's say you have a complex algebraic variety V, and then you consider this group, the group, abelian group consisting of all constructible functions on your variety. So these are functions of the form this, where you take a linear combination, integral linear combinations of subvarieties, like that. W is a closed subvariety of V, and in front of it, we have an integer. So that's a constructible function, and the collection of all such things form a group. And then this assignment of group to each algebraic variety defines a functor in the following way. Whenever you have a proper map between two varieties, then you have a group homomorphism from in the right direction. So you have a group homomorphism from constructible functions on V1 to constructible functions on V2. So what is this group homomorphism? I only have to define it for the generators, which is a functions of the form 1W, where W is your subvariety. And then I'm going to define the push forward of this 1W to be the constructible function on V2, which is given by this formula. Whenever you have a point in the target, V2, you look at the fiber, intersect with the given variety W, and take its topological Euler characteristic. That turns out to be a constructible function in the sense of previous slide, and it defines a group homomorphism. So it was predicted by Grothendieck and Deligne that there should be a natural transformation from this functor, the functor of constructible functions, to the usual, say, singular homology theory, which are both covariant functors, with the normalization that whenever you have a smooth and complete variety V, and if you look at the constructible function 1V, the value of this constructible function under this theory is the usual homology Chern class of such smooth and compact V. And it became a theorem of MacPherson, or the construction of MacPherson. But if you believe that such a theory exists, then uniqueness is not so hard to see. And in fact, the uniqueness argument, in fact, shows that in principle, it shows how to compute in very concrete situations the Chern class CSM of 1W, say when W is any subvariety of your given variety V. So let me roughly show you how that would go. So you want to compute this homology element, CSM, associated to 1W. Then here's one way of doing it. Well, you stratify your W into non-singular part, and by induction, you argue that it's enough to compute CSM of the largest stratum, the smooth part, smooth open part, let's say W naught. And then you consider any resolution of singularities which make the boundary normal crossings. So you have your resolution of singularities, W tilde, and at infinity you see several divisors, Di, which meet in a transversal way to each other. And then because of this normalization for smooth and compact case, and all these properties that are required to this theory to have, you see that the CSM class of the smooth part are already determined by all the other ingredients. So the open parts are not changed by the resolution of singularities. And then you can write at the level of W tilde, you can write this constructible function, 1W circle, as a linear combination of the 1 on the whole variety and inclusion-exclusion formula. But the point is that since we have chosen a normal crossing resolution of singularities, all the intersections of DIs you see in here that are smooth and complete. So we know what their Chern class should be. So you split up all these sums, and you see that each sum end is determined by the normalization. So you see that the theory is uniquely determined by the requirement that we have made. So let's just say that whenever I have a locally closed subset W of an algebraic variety V, the Chern class of W is simply the value of 1W under this theory CSM. It's an element in the homology, and it tells something about my subset W. Well, as we have seen before, by construction, one of the very basic and main property that this theory enjoys is that this inclusion-exclusion principle. Whenever you have two subsets, W1 and W2, if you add the Chern classes of W1 and W2, then you can do inclusion-exclusion. For example, in this very basic case, you get the Chern class of the union and the Chern class of the intersection. Well, this seemingly very naive equality is, in fact, very useful because whenever you want to use such a theory in connection to combinatorics, where this sort of inclusion-exclusion type counting principles are abundant, then the usual theory of Chern classes mostly does not suffice, because even if you have non-singular and compact W1 and W2, the thing you see in the right-hand side, the union or the intersections, are usually singular or non-compact, or both. So the general idea that I would like to convey today is that this general theory of Chern classes connects geometry with combinatorics quite tightly, and this connection is often very useful from a combinatorial perspective. And this connection can be used to prove some purely combinatorial statements that are hard to prove by other methods. So before going into this Schubert varieties and their Chern classes, so I'll try to demonstrate this principle by my favorite example, the chromatic polynomials of graphs. So let me remind you. So this is a one variable polynomial associated to a finite graph. So whenever you have a graph, pick your favorite graph and consider this function chi of a g. That's a polynomial in one variable q, which counts the number of proper q colorings of your g. So you have q colors, and you're using two different colors to color the vertices, and whenever they are connected by an edge, you're required to use two different colors. it turns out that this function is in fact a polynomial in Q and with integral coefficients. Well, whatever it is, it's a very universal object. It's defined for any finite graph. And this is perhaps the simplest non-trivial example. We have a cycle on 4 vertices, and it turns out that the polynomial, the universal counting polynomial in this case, turns out to be this quadratic polynomial with alternating coefficients 1, -4, and 6, and -3. But if you want to actually compute this chromatic polynomial for a given graph, what would you do? There is only one natural way of doing it, namely the so-called deletion contraction algorithm. What you do is the following. You pick one of the edges, whatever edge, it always works. You pick one of the edges, say in this case the one on the top, and you form 2 new graphs, the first one being the graph with that edge deleted, and the second one with chosen edge contracted. So you have a pair of graphs out of the original graph, and you formally write the original graph as the difference of 2 graphs, deleted one minus the contracted one. But the observation is that if you compute the chromatic polynomial of 3 and compare them, there are obvious recursion relation. The chromatic polynomial for the original graph is the difference of the 2 graphs, G prime, the deleted one, and G double prime, the contracted one. So the graphs that you see on the right-hand side have both smaller number of edges than the original graph. So you have an algorithm to compute these. But what you have seen in this slide is really the principle of inclusion-exclusion in disguise. So let me rerun this example from point of view of certain algebraic varieties to associated graphs. So that algebraic variety would be the complement of certain arrangement of hyperplanes in a projective space. And I'm going to write it by d of g. And the point is that it's very easy to see that the Chern class of this arrangement complement is, in fact, this chromatic polynomial of the graph. And the non-trivial step, which is where the geometry became truly useful, is that by studying the geometry of the arrangement complement, you could say fairly non-trivial facts about the chromatic polynomial, which are hard to explain by just looking at the combinatorics of the graph. So for example, one fact would be that these coefficients form a sign-alternating low-concave sequence for any finite graph. Well, whatever that means is a numerical inequalities that are supposed to be valid for all finite graphs. So it should be something fairly it should be something quite straightforward. It's a statement about all graphs, but somehow no combinatorial proof of that simple numerical inequality is known so far. So let me show you the inclusion-exclusion in this case. So the variety in question is this. You introduce one variable for each one of the vertex, and whenever you see an edge, you introduce a hyperplane saying that xi is equal to xj. So one variable for one vertex, one hyperplane for one edge. You remove them all, and you observe that in the process of doing deletion contraction, deleted graph G prime, contracted graph G double prime, you see a decomposition of this triple of arrangement complements into disjoint union. If you form the complement associated to a deleted one, which has one less hyperplane, then you see that it's a disjoint union of 2 things. The arrangement complement of the original graph, and at infinity, in the hyperplane that you have deleted, you see again arrangement complement of one smaller dimension, which is exactly the one associated to the contracted graph G double prime. So by this formal reasoning, you have this Chern class of dg prime is equal to CSM class of dg and dg double prime. And if you identify the homology group or cohomology ring of the projective space with a truncated polynomial ring in one variable, then you should believe that up to appropriate choice of basis of this truncated polynomial ring, this Chern class should be the chromatic polynomial of Q. There's simply no other choice because they are given by the same algorithm. So the non-trivial geometric fact that can be used to deduce statements about the chromatic polynomial, and in that case was the fact that this algebraic variety, dg, admits many, many differential one forms. The point is that whenever you have arrangement of hyperplanes, sufficiently many so that there are no common intersections, then you can use the defining equations of the hyperplanes to embed the complement into algebraic torus, c star to the n, where n is the number of hyperplanes. But c star to the n being a group that has many, many differential one forms, and differential one forms can be pulled back. So whenever you have arrangement complement, you have many differential one forms, in fact, which is sufficiently general in the sense of our first slide. So that tells us something non-trivial about the Chern classes of dg. Whenever you have this theory of generalized Chern classes, to be able to speak about Chern class of non-compact variety dg like that. So what's happening for the Schubert variety case is exactly the opposite. You have a Schubert variety, which is by definition b-orbit closure on some variety. So it has lots and lots of vector fields generated by this large group action. So you expect your Chern class to be positive as opposed to the previous case, which are negative. So this negativity, the presence of differential one forms, was responsible for the fact that these chromatic polynomials are sign alternating, plus, minus, etc. The presence of many vector fields, that's responsible for the positivity of the numbers that you have seen in the first slide. Okay, so let's go into the Grassmannians. So let me introduce some symbols. So you fix a complex vector space, E, of whatever dimension, and then you look at the set of all d-dimensional subspaces of your E. So the collection of all such, and that's the Grassmannian that I'm going to write by gr of sub of D. That's supposed to be the dimension of my subspaces. And inside that Grassmannian, I have these Schubert varieties given by partition of an integer into d parts. Whenever I have a list of decreasing non-negative integers, then such alpha determines the Schubert varieties, parametrizing d planes which satisfy certain incidence conditions with a flag of subspaces determined by partition alpha. Well, the point is that this Grassmannian is a disjoint union of Schubert cells, which is a set of all d planes which strictly satisfy these incidence conditions, and each cell is isomorphic to affine space, and that decomposition gives a distinguished basis for a homology group of Grassmannians with integer coefficients, giving you the fact that whenever you have a homology class inside the Grassmannian, that's uniquely expressible as an integral linear combination under this distinguished basis of Schubert varieties. So a homology class in the Grassmannian are simply a list of integers. So when I have a Schubert variety S alpha, then that's the closure of the Schubert cell that I'll write by S alpha naught. And that's a collection of d planes, which is isomorphic to affine cell. And in particular, I can take, by this general theory of Chern classes, I can now speak about Chern classes of Schubert varieties, or even I can speak about Chern class of Schubert cell. I have a constructible function which is 1 on the Schubert cell and 0 outside. And that's a certain homology element in my group. And that's uniquely expressible as an integral linear combination. And you see that you get a well-defined integers, gamma, indexed by two partitions. One partition, alpha, that gives you the Schubert variety, and the second partition, beta, which are smaller than alpha, which gives you the coefficient of Chern class of S alpha in front of the class of S beta. So these numbers, gamma, alpha, beta, are the numbers that you have seen. There's one for each pair of partitions. And the conjecture is that these numbers are non-negative. Of course, you can ask the same positivity question for Chern classes of Schubert varieties instead of Schubert cells. But in fact, the positivity for Schubert cell is strictly stronger than the one for the Schubert variety. Because whenever you have a Schubert variety, then that's a disjoint union of Schubert cells. So the positivity for Schubert cell would imply the positivity for Schubert variety. So let's focus on Schubert cells rather than varieties. Here is one promised expression that determines all these numbers, gamma, alpha, beta, in one formula. So we have a whole array of these numbers, gamma, alpha, beta. And the explicit expression for all these numbers at once, obtained by Aluffi and Mihalcea, is this. If you want to know this gamma, alpha, beta, you look at the coefficient in front of t to the alpha and u to the beta in this large generating function, formal series, in two sets of variables t and u. And that's your number. So depending on your taste, this formula is really beautiful or horrible. But anyway, in that single line, all these numbers, gamma, alpha, beta, are there.
So the dimension of the vector space does not enter.
Yeah, it's not there. So yeah. Only D is at the formula, which is the dimension of the subspace. Well, anyway, that's what they are. So if you don't like it, I'll give you the second version of the explicit expression. And that's this. So I made it into a very small font so that you cannot read it. So let me read it for you. So this time, this is a formula for individual coefficient, gamma, alpha, beta. So you give me two partitions, alpha and beta, string of integers. Then I say that gamma, alpha, beta is a sum of certain integers. And that integers are determinants of certain matrices. What is that matrix? Well, it's a large matrix, D by D matrix. And the entries are certain binomial coefficients. All the entries are binomial coefficients. What are those binomial coefficients? It's, of course, determined by alpha and beta, but there are certain Lij's. Lij comes in the sum expression, and the sum is over all strictly upper triangular non-negative integral matrices Lij, which satisfy a certain collection of linear inequalities determined by alpha. And that's your gamma, alpha, beta. So I have did this for one example, and I'll show you the result. So whenever you have a partition 3, 2, 1, and 2, 0, 0, if you read the previous sentence very, very carefully 5 times, and then run this computation, then it says the following. Gamma, alpha, beta is a sum of 12 numbers, each one of which is a determinant. And the matrices that comes into play are these 12 matrices. All the entries are binomial coefficients. And the point is that if you do this, compute the determinants, you get 3, 2, 2, minus 1, 2, 0, 0, 2, 0, 1, 0, 0. Sum ups to 11. But the point is that this formula is not a positive formula. It often happens that one of the summands are negative. But the claim is that if you sum them all according to this scheme, all these negative entries are eventually cancelled out by some mysterious reason, and the final output is always non-negative. So here is what I mean by a geometric proof of the non-negativity. The main result is this. You fix a partition alpha and look at the corresponding Schubert variety. S alpha, that's a compact variety, possibly singular, and choose an integer k less than the dimension. And you look at the k-dimensional part of the Chern class of the Schubert cell. It's a certain k-dimensional homology element inside the vector space or the group of homologies of Grassmannian or Schubert varieties of S alpha. And the claim is that this is actually a fundamental class of a certain reduced and irreducible k-dimensional variety indexed by alpha. There is a reduced and irreducible k-dimensional variety whose fundamental class is the k-dimensional part of the Chern class. Well, why does this imply that all these numbers, gamma, alpha, beta, are non-negative? Well, because this so-called effective cone of cycles in the Grassmannian case, in the Schubert variety case, is very simple. Whenever you have such a homology element, if you write it in terms of this canonical basis, all the coefficients that you see are non-negative. But still, that does not tell us much about what these numbers actually are. So, but as I said, I use very little about this special property of Schubert varieties in Grassmannians. So let me try to tell you what's going on behind the statement in general. So there's only one special fact I'm using about Schubert varieties in Grassmannians. And whenever you have all these properties, you have the corresponding statement. So let's be quite general. So let's say B is your, say, connected affine algebraic group acting on whatever irreducible projective variety Y with an open dense orbit, Y naught. Our previous example would be the Schubert variety being the B orbit closure. And the property that I want is that these varieties with open dense B orbits have a very nice kind of resolution of singularities that respect the group action. So I'll say that equivariant resolution of singularities about my projective variety Y is B-finite. Well, it is a normal crossing resolution in the usual sense. So it's isomorphism on the open dense orbit, and the complement is a union of divisors which meet transversally. The main point is that I require my equivariant resolution to again have finitely many B orbits. So this is, I mean, all our favorite varieties that arise from this group action context usually have, whenever you have open dense orbit, they usually tend to have finitely many B orbits. But that's not in general. It is possible that you have a projective variety with open dense orbit, with finitely orbits in general, but whenever you try to resolve it in an equivariant way, in whatever equivariant way, you are forced to produce infinitely many B orbits at infinity. That could happen. So I want to avoid that. So that was the definition of B-finite log resolution. And the fact that you can deduce from the existence of B-finite log resolution is this. Whenever you have a B-finite log resolution, the Chern class of the open dense orbit is effective, meaning that it's a non-negative linear combination of fundamental classes of subvarieties of right dimensions. So in other words, Chern-Schwartz-MacPherson class of the open dense part is represented by an effective cycle if Y has a B-finite log resolution. So this is one of the facts that are needed to argue in the Schubert varieties in the Grassmannian case. They do have such kind of resolution of singularities. Well, in fact, they do have one further nice property that I call B regular. Which is a B-finite log resolution, such that every B orbit of the resolved variety has a point fixed by a maximal torus of B. Well, again, it turns out that Schubert varieties in Grassmannian have such kind of resolution of singularities. And the fact that you can deduce from the existence of such even nicer resolution of singularities is that the statement that you have seen before. If you have a B regular log resolution, there is a reduced and irreducible k-dimensional subvariety whose fundamental class is the k-dimensional part of the Chern class of the open part. So it's not just a non-negative linear combination of classes of subvarieties, but it's rather the class of a single reduced and irreducible subvariety of right dimension. And you can, in fact, such choices of such subvariety Z comes in families, so it moves in large families, as you would expect because of this group action. And it even moves further, and you can write it quite explicitly. So it generically lies in the open part, and it's determined by a choice of a sufficiently general k plus 1 dimensional subspace of the Lie algebra of B, and it's given by, on the open part, it's given as a collection of points where the intersection of the given general subspace of the Lie algebra intersects the isotropy Lie algebra at the point y in a non-trivial way. So it's a certain degeneracy loci, as you would expect, because of this connection to Chern classes. But what's puzzling is that you don't have this sort of nice resolutions for Schubert varieties in more general flag varieties like G mod B, even type A. We're not talking about crazy objects. You have flag varieties, FL4. Then what's happening is, of course, you have a Schubert variety. You have finitely many B orbits. It may have singularities so that you want to resolve it. Let's say you have a singular point at the B fixed point. Well, there are finitely many B orbits in total, and whatever equivariant resolution process that you have in mind, well, at some stage you have to do something about this singular B fixed point. But the point is that if you look at the tangent space at this B fixed point, then our group B acts on this vector space, and that action may have infinitely many B orbits. So if you blow up this singular point, all these infinitely many, infinitely near orbits spread up and show up in your resolution. And it shows that you cannot, well, at least in your choice of resolution of singularities, you cannot achieve finitely many B orbits upstairs. For some mysterious reason, you could avoid that for Schubert varieties in Grassmannians. Well, yeah. Well, I don't know how to make this precise, but I think it's a true statement that most Schubert varieties in general flag varieties, say in G mod B, do not have B finite log resolutions. But if you have Grassmannian, Schubert varieties in Grassmannians, then in fact you could find a very simple resolution. In fact, they are resolved by Schubert varieties in some partial flag varieties which have finitely many B orbits. And that shows our previous statement on the effectivity and this reduced and irreducible representative for Chern classes. That's right. I don't know. So the resolution I have in mind only works only have a clear analog for the Grassmannian case. Well, but still, something interesting happens in this case. So, one obvious case where you have all this positivity for this Chern classes of the open part is that when you have a resolution of singularities with all these good properties, and if you look at this logarithmic tangent bundles, the T of minus log D, then if they are globally generated, all my assertions are fairly standard. But even in the Grassmannian case, these resolution of singularities do not have globally generated logarithmic tangent bundles. But still, their degeneracy loci are as if they are globally generated. So there's some fine line in this layer of positivity that you can ask about these generalized tangent bundles. So anyway, let me end my talk by reminding you some of the obvious problems that you can ask out of this story. The first is explicit formulas for Chern classes of B orbits in G mod P, the ones analogous to the one you have seen, this formula of Aluffi and Mihalcea. So if you are one of those people who tend to think that such formula is very beautiful, then I suppose you will have also quite beautiful formula in the general case also. And the second thing that you can pursue is, of course, this combinatorial proof, or even better, algebraic proof of this non-negativity. Even just in the Grassmannian case, we don't know. And if the general case of this non-negativity is true, then you could aim for a general proof in that approach. Well, these numbers are fairly natural and very canonical. So whenever you have an orbit closure in flag variety, you have all this collection of numbers, and which seem to be positive. Oh, it's hard to believe that those positivity are accidental. It should be dimension of some algebra or something like that. So I think it's quite probable that more can be said concerning Chern classes of Schubert varieties. And concerning this existence of special type of resolution of singularities, of course, you could also dream about the existence of some very neat combinatorial characterization, which tells you which one of Schubert varieties have B-finite log resolutions and which ones do not have. So you can distinguish, in principle, you could distinguish Schubert varieties into two classes, those ones which have truly finitely many B orbits, and those ones that do have, in fact, infinitely many B orbits hidden inside their infinitely near points. So there might be a neat combinatorial characterization. So this is really a statement about the singularities of Schubert varieties from a group theoretic point of view. And the fourth one, which is, I think, is most interesting, but a little bit distant from the main flow here. I have told you that if you look at this Chern class, the element in the homology group of the Grassmannian, I said that it's the class of a reduced and irreducible subvariety, and not just a linear combination of such things. So you could, in general, think about these prime cycles in the homology of G mod P. Well, the effective cone, the cone of all effective cycles in the homology of such things are, well, rather trivial in this G mod P setting, but the distribution of these prime cycle classes are very mysterious and I think very difficult. But it would be very nice if you could say something roughly how these primes are distributed and what kind of conditions that they should satisfy in addition to effectivity in this case. Oh, that would, for example, tell you further about our coefficients gamma, alpha, beta, other than non-negativity. So it appears to me that inside this large effective cone of Grassmannians, only a fairly small region are occupied by these prime cycle classes, and meaning that all these gamma, alpha, betas, for example, should satisfy much, much stronger inequalities than gamma non-negative. I think they should satisfy some sort of quadratic inequalities, etc., etc. So you don't expect the complete characterizations of primes in the homology of such things, but maybe up to a multiple or something like that, you could say roughly how they are distributed. And these explicit expressions that you obtained here could be a motivating set of examples how these numbers are distributed. So I'll stop here. Thank you for your attention.